Somebody wrote in, the world needs a sign like this. Russell had come from MIT with John McCarthy when he came to Stanford. We tried to organize a space war competition between MIT and Stanford, but the phone lines were too slow to handle the communication. In 1964, I was privileged as a graduate student to go to the meeting organized by these 6 men. This was the Gatlinburg Conference on Numerical Algebra, organized by Alston Householder, the 4th person from the left in this picture. All 6 of these men did mathematics that eventually contributed to MATLAB. We have Householder transformations and Gibbons transformations in MATLAB. Wilkinson was responsible for the algorithms that we use in MATLAB. The man on the far right, all 6 of these men are now passed away. Bauer was just passed away just last June. Bauer was from Munich, Germany. He was responsible for the primary author of the ALGOL report that defined the international algorithmic language. That was the framework for much of the work on computer languages. As you'll see, MATLAB is actually a derivative of ALGOL, the MATLAB language. Here's a page out of my thesis that I wrote under Forsyth's direction about computing the eigenvalues of the Laplacian. And I use this as my example, this L-shaped domain. We were interested in it because the reentrant corner, the 270-degree corner, causes a singularity that posed problems for finite difference methods. This domain, and that plot I did on a CalComp plotter, which had a large piece of paper on a drum, which moved back and forth, and a pen, ballpoint pen, which moved around on the paper and plotted on it. And we could draw contour plots. And that was the plot, the way we did I did the plotting. That page of computation took a half an hour to compute those numbers on Stanford's mainframe. That became the MathWorks logo. We're the only company in the world that has the solution to a partial differential equation as our company logo. Here's how it evolved over the years from that CalComp contour plot, 2-dimensional black and white wireframe, and then adding primitive color and finally lighting and shading to the logo we have as the company logo today. Forsyth taught a course in numerical analysis course and wrote some notes about matrix computation. I taught the course as an instructor. Those notes turned into this book that was later cited as an important book by the ACM because it contains actual code. There are programs in this book in Fortran and ALGOL and PL1 for solving systems of linear equations. That would later become MATLAB's backslash. Wilkinson visited the United States every summer, taught in a short course at the University of Michigan, and then went to Argonne for a project I'll tell you in about a minute. Here he is lecturing at Argonne. Wilkinson was working on algorithms for doing matrix eigenvalue computation. When Wilkinson started his work, people didn't really have reliable algorithms for computing matrix eigenvalues. But in his career, developed those algorithms. His work was published in the journal Numerische Mathematik as ALGOL procedures for doing these matrix computations. His work had, other people worked on it. There were a number of algorithms published, and they were collected in this book by Wilkinson and Christian Reich. You notice that Bauer is the editor. This book is still a book you can read today if you want to see how matrix computations are done. This is a very readable book to go read the algol programs here. It's impossible to read the Fortran programs or the C programs that we actually use. They're so complicated, but you go read this book, go read the algol programs, you can see what the algorithms actually are. But you can't actually run them because nobody has an algol compiler today. So the project at Argonne was to translate those into Fortran. And that became the IcePack project for Eigensystem package. This group at Argonne worked on translating the algol into Fortran and then certifying that Fortran, that is, run it on machines in a number of laboratories and universities, and then develop a project for actually distributing that code. I was a part of that project in my summers when I was a university professor, and this is the guide, the user's guide to that collection of Fortran programs. That was followed by the LinPack project to do linear equations. This is a matrix on the front cover. I invite you to compute the inverse of that. It's on the back cover. You can check with me. When I gave this talk in China, a young student actually did that and came up to me afterwards. It's the only time anybody's actually taken me up on that challenge. Here's the four authors of the LinPack manual. There they are, Dungera, Moeller, Stewart, and Bunch. Here we are in 1979. That's Dungera's car with a LinPack license plate. Here we are 33 years later. Dungera's lost the most hair, but I have the coolest shirt. This is the beginning of the LinPack benchmark. Today, LinPack is known as a benchmark. It's famous as being a benchmark. It started out as a software package, but we sent the software around to this list of laboratories and universities and asked them to run the programs to make sure they worked, and then to time one of them. To time, somewhere on this list, time DGEFA, which solves a system of linear equations, 100 by 100 system of linear equations. That's what was the memory capacity of the mainframes at that time. 100 by 100 I can't time on my machine today because it's less than one clock tick. But that was the capacity of these machines, except Yale. The machine at Yale couldn't handle 100 by 100, that was too big. So we had to do it by 75 by 75 and extrapolate. The fastest, these numbers scribbled in here by Dungera calculated the megaflop rate of these machines. And the fastest machine in the world was at National Center for Atmospheric Research, and it was doing 14 megaflops. This was 1979, maybe 1978. Today, the fastest machine in the world is 9 orders of magnitude faster than that. LinPack is still the basis for deciding what's the fastest machine in the world. Today, it's now called the Top 500. And it's a website where twice a year, they declare who's the fastest machine in the world. It's getting pretty boring because this machine in China has been the top machine the last 6 times. It's been the top the last 3 years. It's now getting so they get these monstrous parallel machines with thousands of processors. And you can just run it for a couple days and get a big Linpack number and become the fastest machine in the world. And our national laboratories at Oak Ridge and Livermore and Los Alamos just don't bother. It's just not worth it to run it. I'm blocking on his name now. The guy who runs the lab at Oak Ridge, he tells me he can, when he comes to work in the morning, he can tell whether they'll run in the Linpack benchmark by looking at the steam that's coming out of the cooling towers. Anyway, so that's the Linpack benchmark, is solving a huge system of linear equations. This is where it got started by those scribbles in the column from the appendix of the Linpack manual. 1979 was also important because of this, a Star Trek movie. But now I've got to tell you a story and go back a couple of years. Let me get out of here and tell you about the singular value decomposition. In 1976, I made a movie at Los Alamos. I was at the University of New Mexico, consulting at Los Alamos Laboratory in New Mexico, and I made a movie about how you compute the singular value decomposition. And let me play a little bit of this movie. No, this one. This is 6 minutes long. I don't want to play the whole thing.
Here, Tacoma, Washington. What?
Pardon? Oh, it's not on there. Why isn't it on there?
Well suited to solving problems involving large matrix.
So I have to do something.
Volunteer.
Why am I not getting the movie?
Yeah, it's not bad, but good.
Oh, goodness. Let me get back to that. I'll go back and tell the story of the movie, show you later. The movie isn't showing up.
Okay, so this one? Or which,
Well, I'm gonna wanna show both of them.
which one is it? Just double click on. Oh, has it gone back to extended? Yeah, for some reason. Sure, it's okay. How do you move this?
sound.
That's right. Say that.
Um,
Sound not working.
You can give us the commentary.
It has something to do with the sound over here. But
Is there any other sounds? Oh,
Interactions on the overall system.
thank you.
Oscillations may be generated. Matrix analysis can describe.
So,
The computer is used to simplify the matrix so that most of the entry.
so this was a film about computing the singular value decomposition. How many people know what the singular value decomposition is? A few of you, half of you. So in 1976, the singular value decomposition was new. It was fairly new. The algorithm was new, and this film was about how the algorithm works. Also, the graphics techniques here were new. Putting Greek letters on the screen was new. And the hidden lines algorithms you're going to see in a minute were new. So I was working with the Los Alamos graphics people to do this film. And even this
It will be
little part,
zeros.
doing
One
this,
method is known as the
doing
singular
these
value
Greek letters
decomposition.
was something that was
The
new.
original matrix is represented as the product of three matrices. In the second of these matrices, the only non-zero elements lie on the diagonal. These elements, the singular values of the matrix, determine the frequencies of oscillation of the original system.
Well, they don't. The singular values don't.
The other two
determine the
matrices
frequencies.
must preserve the properties of the original matrix.
So-
The diagonal of the matrix.
So here's
from
the
the upper
matrix
left to the lower
represented
right.
as these triangles. And
Orthogonal
we're
transformations
introducing,
will be used to introduce
using
zeros.
Givens transformations to introduce
The
zeros.
initial
in the
transformations
matrix.
put zeros into the first row and then the first column. Each transformation affects two other columns or rows, shown here in blue. Later transformations introduce zeros into later rows and columns, while preserving the zeros already obtained. Oscillation is a repetitive or iterative process which reduces the size of the
Anyways,
remaining
I
off-diagonal
won't take
elements,
time to show
but
the
does
whole
not
thing.
zero them in a single step. During most of the other off-diagonal elements are also being reduced in size. Once a few of the singular values have been obtained, the off-diagonal elements have become so small that each of the remaining singular values is obtained with a single iteration. The final diagonal matrix, together with the two transforming matrices which produced it, then provide the basis for a complete analysis of the original matrix and the system which it models.
Anyways, sorry it took so long to get to that. But that's a 6-minute film about the singular value decomposition. I've now put that film on the web, and if you want to see it, just you can Google Moeller SVD film or something like that, and you'll get to a YouTube thing about that. Shortly after that, the producers of the first Star Trek movie came to Los Alamos, and they wanted graphics to use on the bridge of the Enterprise as it was going about its business of saving the universe. And so here's a clip out of the first Star Trek movie. This is they're trying to go find the the source of these signals that are coming out of the center of this huge nebula. Look over Spock's shoulder. There's the singular value decomposition being computed on Spock's scope.
A maximum phaser strike directly at the beam might weaken it just enough for us to break free.
Break free of where, Commander? Any show of resistance would be futile, Captain.
We don't know that, Mr. Spock. Why are you opposed to try? Why bring us inside? Not to destroy us. They could have done that outside.
They still can.
Curiosity, Mr. Decker. Insatiable curiosity.
All right, okay. So that was a lot of trouble to show that. Okay, let's open up the windows again, because that's all we've got to show. Thank you. The computations of the singular value, MATLAB didn't have it, but MATLAB was just beginning to, well, I was just beginning to work on MATLAB then. MATLAB didn't have any graphics. The graphics in that movie were not done with MATLAB. They were done with software at Los Alamos. But the computations were done with a very primitive version of MATLAB. And because I was working on it. I read this book by Klaus Wirth. Klaus Wirth had developed Pascal, which was a kind of sanitized version of ALGOL that could be used in teaching and could actually be compiled. And then he wrote this book, which had an even simpler language called PL0. And I learned how to parse programming languages. And I wrote MATLAB as a version of PL0 that had only one data. PL0 had only one data type, an integer. And so MATLAB had only one data type, a matrix. It's a strongly typed language. It had only one type. And it was written in Fortran. I made Fortran recursive. And that was the first version. That was the beginnings of MATLAB. So it's a derivative of ALGOL. That's why the subscripts start at 1, because they started at 1 in ALGOL. And they started 1 in ALGOL because they started 1 in mathematics. Here's if you type, here's a screenshot of the first version of MATLAB. If you typed help, this is what you got. This is all the functions in the beginning MATLAB. There are 80 of them. It's just a few functions out of LinPack and IcePack. There are no ordinary differential equations. There's no FFT. There are no M files. You can't write M files. There are no toolboxes. There's no graphics. It's just this simple matrix calculator. It's not a programming language. Here's something you could do in that beginning MATLAB. This was what, it did have a plot function. It was kind of a joke. This was portable machine independent graphics back then. In 1979, I had a sabbatical. I visited Stanford. I taught the graduate numerical analysis course. Half the students in the class were math and computer science students. They were not impressed. This was not advanced numerical analysis. It was not advanced computer science. Nick Trefethen was in that class. He claims now that he was impressed. I'm not so sure he was. Randy Levesque was in that class. It was a pretty impressive class of students. The other half of the students were from engineering, and they loved MATLAB. They were doing things that I didn't know anything about. They were doing control theory and signal processing, in which matrices were the language that they used. And they'd been writing Fortran programs, they'd been doing computations by hand, and they immediately adopted MATLAB for the things they were doing. They went off to two companies that had spun off the Stanford Electrical Engineering Department, Integrated Systems and Systems Control, and those two companies developed commercial products to do control design automation. The products were called Matrix X and Control C. They were built on top of my Fortran MATLAB with my permission. The primary engineer for Control C was a guy named Jack Little, a Stanford EE major. He hadn't taken my class, but a friend of his had taken my class and showed him MATLAB. Little threw away all his Fortran programs and started using MATLAB. He came to me in 1984 and said he wanted to start a company based on MATLAB. He quit his job at SCT, went up into the hills behind Stanford, threw away all my Fortran, and re-implemented MATLAB in C, which was brand new at the time. A friend of his named Steve Bangert had a wife and kids. He couldn't quit his job, but he worked on MATLAB on the weekends. And the three of us founded MathWorks in California, in Silicon Valley in 1984. Little and Bangert put in M files, put in graphics. Little wrote the first control toolbox, wrote the first signal processing toolbox. I wrote some of the documentation. The three of us founded MathWorks in California in 1984, and MATLAB made its commercial debut at a control conference in Las Vegas just before Christmas in 1984. Little with his own money bought this machine, an IBM, a compact machine compatible with the first IBM PC. Oh yeah, Little had anticipated that the IBM PC was going to be possible to use it for these kind of computations. The first IBM PC had only half a megabyte, actually 640K memory, which was hardly enough. You could only have, I don't know, a handful of 90 by 90 matrices in memory. But his first machine didn't even have a hard drive. You had to take 5 1/4 inch floppies and swap them in and out. Jack and Steve programmed MATLAB on these machines, and they were the first machines for MATLAB. Little was the first employee of MathWorks in 1984. That's 2 to the 0 employees. Banger joined the company the year later, giving it 2 to the 1 employees. And the company doubled every year for the first 7 years. Since then, we haven't doubled as fast, otherwise we have now 2 to the 32nd employees. And we'd have to hire 2 to the 32nd more again this year. Here's a plot, log plot of the size of MathWorks over the last 32 years. We now have, I've got to update this plot. We now have close to 3,500 employees around the world. Here we were when we had 2 to the 3rd employees. That's a little down the bottom. Lauren Shore, who so many of you know. Jim Tung, Jack's wife in the pink coat. Here's when we had 2 to the 5th employees. I wasn't an employee of the company for the first 5 years, but I joined it in 1989. There's me. There's Little over in the corner up there. This was our office in South Natick for a while. We almost bought that building. That would have been a mistake. Do that. Here we are. Here's a couple of pictures of us 2 years ago when we had our 30th anniversary in San Diego. We had 3,000 people in a hangar at the Marine Air Base. So we now have 20 offices around the world, including this one here in Australia where we have about 24 employees. We're going to have our 10th anniversary lunch today, right after this one, right after this meeting. Here's our offices outside of Boston, on about 12 miles west of downtown Boston. This beautiful campus where we just completed our 4th building there. Now, this is an important slide, but I don't have the time to talk about it. This is how we make our money. We're in the math department here, and you guys know about our business in numerical analysis and matrix computation. That's what I do. That's what many of you do. But we couldn't have 3,500 employees and almost $750 million worth of sales every year just doing that. This is what we do. And that is take that mathematics and apply it to all these different industries. Here's Wall Street finance. Here's bioengineering. Here's image processing, reading a license plate at dusk in motion, in the rain. That's hard. Here's doing chip design and circuit design. There's a laboratory of some kind. All these using MATLAB. These two, to me, represent our bread and butter. This is control. Keeping that thing flying is hard mathematics. And you simulate this thing, and then you develop the control algorithm, and then you download it into that vehicle and drive, and the code that drives that thing was developed from your simulation. MATLAB is actually Simulink, our companion product. Simulink doesn't run in this device, but code generated, the program that's driving it was written by Simulink. This is the Chevrolet Volt. There are 3 or 4 dozen microprocessors in this thing. And they're all programmed, the engineers that developed this sit at computer consoles like the rest of us and run simulations of the controllers in there. We are not designing the not doing the airflow over here. We're not doing the crash simulation. We're not doing the big finite element codes. But all the electronics that go on in this car are being designed with MATLAB and Simulink. They're simulated, first of all, and then the programs that result from those simulations are downloaded and run in this car. Another interesting thing is the Simulink models become the language of communication between the companies that are designing these things. So a designer of some part at General Motors designs a part, and then he hands the Simulink diagram to a supplier and say, build me this. So in addition to the simulation, the diagram itself becomes the specification of what it is you want to build. That never would have anticipated that. And when you go back to that first MATLAB programming language, the fact that it's developed into this kind of thing is really incredible. Anyway, my wife, several years ago now, my wife was looking for a hearing aid for her mother. She went on the web and she says, hey, Cleve, here's a MATLAB graph. Sure enough, this hearing aid company had a surf plot on its homepage. There's a couple dozen hearing aid companies in the world, including 2 here in Australia. And they all use MATLAB for the signal processing and also for models of the ear. Anyway, that to me represents the industries that MATLAB is in. And I love learning about that stuff, visiting some of these places, seeing the mathematics they're using. Underlying all this is linear algebra and ordinary differential equations. Every place is in all the stuff these guys are doing. So that's the end of the sort of main talk. Oh, I've used up most of my time, anyway. I'll tell you what, I'm not going to talk about HPC. Let's just take some questions here. Well,
thank you for this extraordinary history. It goes, it's bigger than, we started earlier than MATLAB, and that's terrific. The history of, I suppose, of matrix computation for the 20th century. That's extraordinary. Thank you so much. So, questions, comments?
yes.
So you've got toolboxes. How do you decide on which toolboxes to start up with?
The toolboxes, of course, we now have, I don't know, between MATLAB toolboxes and Simulink block sets, we have, how many? 85? Yeah, 85 products. We have working for us experts in various areas, and they say, let's build one of these things, and we have people sit around and say, yeah, that sounds like a good idea. In the very beginning, we had external authors that were building these, that were developing these things. Leonard Young in Sweden on system identification, Carl DeVore with splines, so on. Now we've taken over those things and we have them developed in-house. We have big teams. We've acquired a couple of companies, small companies. A company in Glasgow that develops toolbox for telephone 4G LTE. If you're developing equipment, cell towers, equipment for wireless, and you want to see if you're meeting the specs, meeting the standards, you run your design against this toolbox, and this toolbox checks that your design is meeting the standards. Before you actually even build any equipment, all this is done on the computer with your design in Simulant diagram. So we acquired that company. There's a couple dozen people in that company in Glasgow. I visited them when I was in Glasgow. It was summer, fascinating place. We have huge places, potentials for places we haven't touched. We've barely touched biomedical stuff. Huge opportunities there. Financial operations. The guys in finance will try anything. And they're very secretive about what they're doing. We ask them, how's it going? What do you do? They won't tell us. I've been to Los Alamos. I've had connections with the NSA, but the guys on Wall Street are more secretive about what they're doing. So there's all kinds of opportunities there. How do we actually decide? I don't know. You can't, we have advisory boards, we have in the automotive industry and in the signal processing business and in the telephone, in the wireless business, we have committees that come in and we talk to them about what we're doing with our products, give them a preview of what they're doing and what we're doing, and they give us their reaction and ask us for things what we need. It's very interesting to sit in on these meetings where these guys come in from the automotive industry all over the world. These guys are competing with each other, and they're all doing development of products that won't hit the market over the next 5 years. And they're all kind of working on the same thing, self-driving cars that detect danger and brake and steer and so on. And they all know each other's working on this stuff, and they kind of don't want to tell exactly where they are. And they're all using our tools to do this, and they all want to tell us what they need, but they don't want to quite let on what the other got, where they are. So it's very, very cagey about this thing. It's interesting to see. And they all know each other. It's very interesting to sit in on those meetings.
It seems to me that MathWorks has been very successful in growing from a handful of people to a large thing. That isn't always achieved.
Oh, no. It's incredible.
We must have central decision-making somewhere,
Yeah. Well, what's incredible is that Jack Little is still CEO. That he's gone from being the head of the company when he was the only person in the company to being head of the company now. I'm very careful to say that MathWorks is successful because I haven't anything to do with running the company. I am not good at that. Anyway, long-winded answer to your question.
Would I comment? Question? It's interesting that what you're talking about today is something that had enormous influence on our lives. You made it clear that you were not the only one who has caused this, but there's been a revolution for those like me who started with Fortran and ancient computers.
Well,
it's just extraordinary where we are now.
Yeah, it is. It's incredible how much computers have affected everybody's life. You know, it's been central to my life for, 60, 50, over 50 years, well over 50 years. But what's amazing is how much it's affected everybody else's life.
Yeah.
You know, when you see,
It's making numerical analysis much more interesting too, by the way.
Yeah.
It was the most boring subject when I started, when I learned it at first.
when you see the URLs for plumbing trucks, for plumbing on the trucks, who'd have thought that the URL would become such a, when you see cell phone numbers over the huts in Central Africa, the fact that the cell phone number has become the universal identification. People worried about identification numbers, government issued identification numbers. Your cell phone number is now your identification number.
Yeah. Well, I think we've had a very good go from you, Cleve, so I think it's time to wind it up. But
You said-
let me just say
Are we going to have a little tea or something?
yeah. So Cleve will stay around there for a few minutes. We're going downstairs to the tea room where there are said to be hot cross buns. So let's thank Cleve.
Thanks.
very much. Very interesting to see you back. Nice time.
Yeah.